You know, we've all been told the story of autonomous driving as this simple race to just add more and more features, like climbing a ladder from level 2 to level 3 and beyond. But from where we sit, deep inside the engineering trenches, we see what's really going on. And it's not about features. It's a massive fundamental pivot towards something much harder, much more important: resilience. So let's break down what that actually means.
So why does this pivot matter so much? Well, because the market is absolutely screaming for it. This isn't just some tech fantasy. It's a commercial reality. Get this, in the world's biggest car market, a staggering 55% of consumers will ditch their favorite car brand for another one that has better connectivity. That tells you everything. A car's intelligence, its reliability, these are no longer just nice-to-haves. They're the absolute core of the product.
And this brings us to a really critical question. Is this whole race really about the act of driving? Or is the real battle being fought somewhere else entirely? You know, while the public sees this flashy race for features, the true competition is happening on a much deeper level, in the system architecture, in the data pipelines, and in the incredibly difficult quest for provable safety.
And that brings us right to the central idea of this explainer, what we're calling the Great ADAS Pivot. We are officially moving out of an era that was all about just stacking on features and into a new, deep engineering phase that is totally focused on resilience. This is the single most important strategic shift happening in the industry for the next few years.
This slide just lays it out perfectly. The old way was really a brute force approach, right? Add more sensors, chase those higher automation levels with clunky, rigid software, and just grind out millions and millions of miles of physical testing. The new way? It's so much more sophisticated. It's about achieving safety that you can actually prove, mastering how you validate with things like digital twins and data feedback loops, and building the whole thing on a data-driven, AI-first foundation.
Okay, so what specific problems are actually forcing this pivot? Let's take a look at the new engineering battlegrounds. These are the really complex challenges that show exactly why the old approach just doesn't cut it anymore.
First up, we've got a problem that absolutely terrifies engineers and drivers alike: ghost braking. This is when the car just slams on the brakes for literally no reason. And research, particularly in Dutch tunnels, has shown this is a critical and surprisingly common issue in certain environments.
So why does this happen? Well, it's a perfect storm of sensor limitations and a tricky environment. Your standard radars have what's called an elevation gap. They just can't tell the difference between a truck on the road and a fan on the ceiling. Then you add in multipath effects, where radar waves bounce off the tunnel walls, creating all these fake targets, and you've got a recipe for disaster. And the real kicker? Sometimes the software that's designed to ignore these false alarms actually fails in newer, cleaner tunnels, which paradoxically makes the problem even worse.
And this is a brilliant illustration of why simply adding more of the same old sensors is not the answer. The solution is to add smarter sensors. The rise of 4D imaging radar is a direct response to this exact problem. By adding that crucial fourth dimension, elevation, the system can now see a rich point cloud that easily distinguishes between a real vehicle in front of you and a harmless sign overhead. It basically eliminates this entire category of ghost braking.
The second battleground is connectivity, and this is a huge one. For highly autonomous vehicles like robotaxis, teleoperation is an absolutely non-negotiable safety feature. If the car gets confused, a human operator who might be hundreds of miles away has to be able to take control instantly. And let me tell you, this isn't just a software problem. It is a massive network engineering challenge.
The requirements here are just extreme. I mean, research has defined the absolute physical limits for this to work safely. Latency has to be under 300 milliseconds for a round trip. Any higher than that, and a human just loses the feeling of precise control. You need a sustained 36 megabits per second of uplink bandwidth to stream all the video feeds, and the connection needs to be 99.99% available. A single cell network, it just can't guarantee this.
And the final battleground is data. A single autonomous test vehicle can generate a mind-boggling 500 terabytes of data per day. The old way of doing things, just record everything and we'll analyze it later, is physically and financially impossible now. You literally can't hire enough people or build big enough data centers to process that flood of information.
So the solution is a big shift to what's called smart logging. The car itself becomes the first layer of analysis. The onboard computers use triggers to filter for only the most valuable events, the near misses, the disengagements, the weird edge cases. Then, the test engineers can label these events live, right there in the field. The result? A 100-fold reduction in data volume,
which turns engineers from data haulers into high-value quality reviewers.
Okay, so solving these new, really gnarly problems requires a completely new set of tools. And that brings us to our second major point, the complete reimagining of the car's fundamental architecture, and of course the software that runs on it.
The shift to a zonal architecture is probably the biggest change in automotive electronics since the invention of the CAN bus. The old way, with over 100 individual little computers, or ECUs, created this tangled, heavy, and super complex wiring harness. The new way is just elegant. It's like giving the car a brain, a powerful central computer, and a spinal cord with a few big nerve clusters, the zonal gateways. This radically simplifies the whole system, can reduce wiring by up to 50%, and it's what truly enables the software-defined vehicle.
And this new brain also needs a totally new way of thinking. This quote just captures the shift perfectly. For years, the goal was simple: draw a box around a car or a pedestrian. Now, that's just table stakes. The real challenge, the real competition, is about understanding the entire scene, the context, and predicting what those other actors are going to do next.
To get that deep understanding, engineers are deploying a really powerful new toolkit. Bird's Eye View Models, or BEV, fuse all the camera imports into one coherent 3D map. Occupancy networks take it a step further, identifying any occupied space, whether it's a labeled car or just some random road debris. End-to-end models try to mimic human intuition by directly linking what the car sees to how it drives. And the latest frontier, VLA models, use large language models to understand things like a police officer's hand signals, something that was just impossible for older algorithms.
Now, what's really fascinating is that these new tools and architectures aren't being rolled out in the same way across the globe. And this leads us to our final major point, this incredible three-way global race, with different regions taking very different strategic paths to solve these same core problems.
What you're seeing here is a top-down strategic breakdown of the whole thing. Europe's path is really defined by regulation. Standards like GSR2 and Euro NCAP force a very methodical, safety-first approach, focused on protecting vulnerable road users. Then you've got China, which is all about hyper-competition and consumer experience. This leads to this incredibly rapid deployment of features like Urban Navigate on autopilot. And finally, North America, driven by the tech giants and Tesla's data dominance, is playing a high-risk, high-reward game focused on end-to-end AI and commercializing robotaxis.
So, let's bring this all together. We can see that this huge shift from features to resilience is creating new problems, it's demanding new architectures, and it's shaping global competition. But the ultimate goal of this entire pivot, the reason everyone is doing this, is to solve the single most important challenge, building trust, and that goes way beyond just raw performance.
And this is where a really critical safety standard called SOTIF comes in. Think of it this way. Traditional safety was all about making sure the hardware doesn't fail, that the brakes work when you press the pedal. SOTIF is about making sure the AI doesn't fail. It's about ensuring the car is safe even when its systems are working perfectly, but the AI misinterprets the world, like mistaking a wet patch on the road for a real obstacle. Proving this is the new frontier of automotive safety.
So how do you prove an AI is safe in scenarios it has never seen before? You just can't rely on real-world driving alone. It's way too slow, it's expensive, and it's dangerous to go looking for all those rare corner cases. That's why the industry is making a massive shift towards synthetic data. By 2025, it's projected that the majority of training and validation data will actually be synthetically generated in a simulation. This lets engineers test against millions of dangerous scenarios safely and super efficiently.
So the crucial takeaway here is this. The engineering pivot we've been deconstructing is literally transforming the very nature of the automobile. We are no longer just building a vehicle. We are building an AI on wheels, a continuously learning agent that has to navigate the most complex environment on planet Earth.
And that leaves us with the defining question of this entire new era. As cars evolve from simple machines into these learning AIs, the ultimate challenge isn't, can it drive? We're getting closer to answering that every single day. The real question, the one that this entire pivot is trying to solve, is can we prove it's safe? And that is a much, much harder problem to solve.